So a different vein, he's doing the same kind of research in the laboratory. Only a few years ago was it possible to start laboratory simulations of shocks and jets. And he and the collaborators at the University of Rochester are working on simulating jets. They hit return here a couple of times. One more time. There we go. What you do, this is at the University of Rochester Laser Lab, is zap a box here with a laser on two sides, and you form a shock. The shock goes and hits this ball here and rebounds off. And this is exactly what's happening here. You have a protostar with a jet that's hitting a molecular cloud, and the jet's coming here. When you look at it in detail with a space telescope, you see all these ripples and structures, and this is what comes out of the laboratory simulation. Very similar structures, and this is funded by the Department of Energy, and it's a long-term program. So another thing he works on, and this has just been in the last few years, is they're using this new mosaic infrared camera to study molecular hydrogen in the infrared in star-forming regions. This is part of what we call PDR, a photon dissociation region. And this is Cygnus OB2. The nice thing about infrared is you can see molecular hydrogen. Also, the obscuration by dust in the galaxy doesn't affect it much. So you can see things you can't see in the optical. Next slide. The work I do is on planetary nebulae, and this is planetary nebulae are shells from stars that were once like the sun, but evolved into a red giant when they finish using all their hydrogen in the center by fusion. And then in the red giant stage, you have these different shell burning episodes of hydrogen burning and helium burning. And then finally the shell gets ejected, and that's a planetary nebula. And I had a student who modeled this nebula, used, this is space telescope images, and nitrogen, H-alpha, hydrogen, and oxygen. And you can see it has a blue halo and many, many little filaments. Some are nitrogen strong and others are oxygen strong. And by looking at with 4-meter shell spectrographs with very high dispersion, you can see how the nebula is expanding. And we were able to model the nebula. It's like a dumbbell in the center here, and in the outer parts here is like a skirt, versus a torus seen face on. And you can't get this kind of modeling unless you take high dispersion spectra. And the last slide shows what I'm really working on today, most of all, and that is extragalactic H2 regions. And this is a nearby irregular galaxy, and you see 6822. These yellow blobs here are all ionized hydrogen clouds around newly formed hot stars. And with the Spitzer Space Telescope, just before it went warm, because it lost all of its helium last year, we were able to get infrared spectra of these objects, and we looked at the abundance of neon and sulfur using infrared lines for the first time. What this plot is basically the neon ionization versus the sulfur ionization. The red circles here are a spiral galaxy, Messier 83, in the southern hemisphere, which is a very unusual spiral galaxy in the sense that it has only low ionization H2 regions. This green stars are basically H2 regions in a spiral galaxy, Messier 33, which is next to Andromeda, and it's a low luminosity galaxy that has a wide range of ionizations. And here, the little purple lavender points, the triangles, are the H2 regions of 6822, which you can see are the highest ionization. And we were able, because of this high ionization, we were able to get an accurate neon to sulfur ratio, which turns out to be quite a bit higher than the sun. And it's apparent that the solar abundance of neon, which is very controversial, is even more controversial now. And that our neon to sulfur ratio is very similar we get for H2 regions around us in our own galaxy. And so I think this points out we do a lot of varied research, and even if you don't specialize in astronomy or astrophysics, we have a lot of interesting courses for you to take if you want to take some astrophysics electives. So,
Okay, thank you,
all right.
Professor Dufour and